Good afternoon, everybody. Welcome to a Thursday afternoon, Chem 170 with your host, me, Dr. White. And looks like a lot of people are running late, but I'm starting. Check out the video. So let's get to work. That's not what I want. That's what I want. And if you look at D2L, I sent out yesterday the following email last night, and this is also an announcement. On Monday, the 11th, I'll be giving test number 3, and you'll be able to download the password protected file from D2L. That'll be available this Sunday afternoon, maybe even earlier. On Monday at 5 or maybe a little earlier, I will send out an email via email, the password for test number 3 PDF file. You'll have until Tuesday, 5 p.m. So I'll be teaching, obviously, but to finish test number 3, upload your answers to test number 3 and to assignment area D2L. Should take about 40-45 minutes, take an hour and a half to actually take the test. That doesn't include uploading stuff. Now, test number 3 has 9 pages, 10 problems. Some of the problems have multiple part. I have never in Chem 170, never will, do multiple choice. Test number 3 covers carboxylic acids, esters, carboxylate anions, amines, amine salts, quaternary ammonium salts, amides, and heterocyclic compounds. The point breakdown will be 7 points general knowledge, 38 points nomenclature, 60 points reactions. And that will be 105 points. So there's 5 bonus points. We'll have our review this Thursday, which is today, for test number 3. On Monday, we'll have our regular Zoom meeting and lab, or no, labs on Tuesday, regular Zoom meeting. And then afterward, I'll send out the password and you can take test number 3. All right, because I've been Zooming along, special thing, and I'll put out an email this Saturday for a special thing for both this class and the class I teach at COD at 9 a.m. I will have a special office hour for about an hour or so. Excuse me. If nobody shows up the first 15 minutes, I'm out of there. But if you're planning on showing up, email me. That would be a good thing to do. And I'm there to help you if you need any help with anything for test number 3 in Chem 170. Again, that will be this Saturday at 9 a.m. Yes, I'm a morning person. It's optional. All right. That's the first thing. Next thing I want to talk about, as you can see on your screen, and it's available in the assignment area of D2L, is an extra credit project. And this extra credit project is worth 10 bonus points. How do you get your 10 bonus points? Well, you create a chart that contains 10 molecules, which are found in ingredients list of commercially available products. And these products, you can only use a molecule once from the in the chart, but you get up to 3 molecules per product. That's my way of, and by the way, who came in late? Who came in early? Chioma, it's just you and me, but I'm still going on with everybody else. I can introduce here. So I'm pretending we got a full house, but, and what you came in late, you can see on the video. All right, let me get back to what I was talking about. Oh, one thing I got to do. There. And here's that extra credit project. And the extra credit project, like I said, is create a chart with 10 molecules, 10 points, 10 molecules, one per molecule, that are found in an ingredient list of commercially available products. You can use a molecule only once in the chart, and you can only get up to 3 molecules per product, which means 10, you got to look at 4 products. And to get full credit for a molecule, all entries in the row of the chart must be correct. For each entry, record the name of the product, the molecule, and one functional group, or if it's the only functional group that's present in the molecule. Be sure to put your name on the chart. Here's an example. Brand X wine contains ethanol, that's an alcohol. Now, this is important. Listen, you cannot use the following molecules: sucrose, ethanol, isopropyl alcohol, acetone, ethyl acetate, propane, acetic acid, or methane. Everything else you can use. You can't use the following products in your chart: beer, wine, vegetable oil, vinegar, gasoline, propane, natural gas, orange juice, milk, sugar, and butter. Everything else is fair game. If it's got an ingredients list on it, you can use it. Now, this is important. This helps you more than me, because before I put this in, students are always getting functional groups wrong. The ingredients must appear, first of all, on an ingredients list on the product. And this is important. They must contain a functional group we have talked about in class, not one we didn't. There are a bunch we didn't talk. But this way, you're not going to get them wrong, because people do that. Now, this has to be uploaded, and I think I have to change it on D2L, because I had an earlier date and I changed my mind. This has to be submitted. It's due by the end of the day, July 20th of this year. No late projects are accepted. Please upload it as a single PDF file or a Word file. Now, this is optional. You don't have to do it, but if you do it right, you get 10 points. It's like getting 10 more points on a test, or if you missed a lab, 10 points. And this adds to your bottom line 10 points. Now, important thing, beware, not all names on labels are IUPAC or common names. A common mistake I've seen, which is why I put it here, simethicone, O-N-E-N-D. Oh, it's a ketone. No, it's a silicone product compound. And how do you find molecules? Well, and check what functional groups. You can use Google, or you can ask me if you've done some work and you're not sure, and I'll talk more about this in a second. I'll help. Now, to use Google, place the name of the chemical that you're looking for, like ethyl acetate, and then type the phrase chemical structure. One of the first 3 hits you come up with will have the chemical structure. And you do that in the search box. Now, as a special service to my students, I would highly recommend, and this can be just informal, send me your chart before it's due. I'll review it. If there's something wrong, I'll tell you what you got to change. I know that's not a ester, that's a different functional group. And that way, there's no reason, if you do it early and ask for some help from me, you shouldn't be able to get 10 bonus points. Like I said, it's in the assignment area of D2L, but it's totally optional. All right, any questions?
No.
All right, well, I'll move on. I got my full class here. Well, not really, but everybody else can watch the videotape. All right, I promised today, first of all, I'm going to do the review for test number 3, Monday, You're going to be taking it, and then I'll go through the amines and amides and problem set. So I better get to work. All right, everybody see, give me a thumbs up if you see test number 3 review on your screen. Thank you. All right, let's get going. And this is available on D2L. Now scroll to the bottom of the lecture. You're going to have to click on the button, load more, scroll down, and you'll see both as a Word document and a PDF file that it is test number 3 review by me. All right, let's get started. First of all, we have a carboxylic acid, carbonyl hydroxy group R group. How do you name it? You find the longest chain with the carbonyl carbon, name it as an alkane, drop the E, add OIC in the word acid. The carbonyl carbon, when you're numbering to do other alkyl groups, is always number 1, but you don't put that name in number in the name because everybody knows it's number 1. Now, there are 3 common or 2 common and 1 common / IUPAC names you should know. When R is a methyl group, nobody calls that ethanoic acid. It's called acetic acid. And if you take that, mix it with water, you have vinegar. Anybody pick up a bottle of vinegar and say, aha, it's got acetic acid in it, and that's a carboxylic acid? You should. And then when R in a carboxylic acid is H, that's formic acid. When R is a benzene ring, IUPAC said, well, we're not going to change those organic chemists. The common name was also made the IUPAC name, and that is benzoic acid. Now, reactions of carboxylic acids with base. And if you take a carboxylic acid, react it with base, the hydrogen on the oxygen is acidic, proton transfer, you also get water, but you get this carboxylate anion salt. Now, a special base reaction that you should know, which I talked about, the little rocket ship, and that's where you take a carboxylic acid and react it with sodium bicarbonate, which is also known as baking soda. And here I'll ask, give all the reactions. And what you get is a carboxylate anion, water, and carbon dioxide, CO2, given off as a gas. And remember the little rocket ship? And also don't forget, this will neutralize the citric acid in tomato sauce. And that was my father's special secret, one of them, tricks to make really good spaghetti sauce by putting in at the end a little bit of baking powder. Now, also the other thing, which I won't ask on test, is put a little pinch of cinnamon. All right, how do you make carboxylic acids? You take a primary alcohol and oxidize it, O bracket, O close bracket, oxidize, you get a carboxylic acid. The carbon with the hydroxyl group becomes a carbonyl carbon. If you take a aldehyde and oxidize it, same thing, carbonyl carbon becomes the carbon with the hydroxyl group of a carboxylic acid. Now, a really cool way, because you use dry ice sometimes, is if you take a Grignard, where X is chlorine, bromine, or iodine, reacted with CO2, second step acid, and water, you get a carboxylic acid that's 1 carbon longer than the Grignard you started with. Again, if you take a Grignard reagent, react it with carbon dioxide, you get a carboxylic acid that's 1 carbon longer than the Grignard you started with. All right, next I talk about another functional group, and that's an ester. That's where you have a carbonyl with an R group. The carbonyl has an oxygen. On the oxygen, you have more carbons, which we call R prime. How do you name them? For an ester, First of all, R prime is named as the alkyl group it is in the front. And then there are two ways of doing the rest of the molecule. IUPAC, name the carboxylic acid you'd use to make that if R prime were H, and drop the IC and the word acid and add ATE. Again, drop, it's not clear, so let me. Drop the IC in the acid, and to that, add ATE. And then that's how you name it. Now, I should remind you, my promise to you for esters, even though the carbonyl carbon is one, and you name it, it can get very confusing. So I will never on a test or my final for this class put an alkyl group on the R of an ester. R prime is an alkyl group you should know how to name. Now, a student of mine came up with a second way of doing that. When R is not a benzene ring, when it's a benzene ring, you got to use 2A. When it's not, find the longest chain, including a carbonyl carbon, the second part of the name. Name it as an alkane. And now for this method, you drop the E, add OATE. The R prime is still named as the alkyl group in front. I only asked you to learn one common ester, and that's this one, where R prime is ethyl, R is methyl. Nobody calls this ethyl ethanoate. It's called ethyl acetate. And ethyl acetate is a molecule that's one of the two molecules used for nail polish remover. Again, ethyl acetate is one of the two molecules used for nail polish remover. Now, another derivative of carboxylic acids, which we talked about up here, when you react it with a base right here, this is a carboxylate anion. And how do you name a carboxylate anion? Well, the cation you name as the element it comes from. And for this class, M could be lithium, sodium, or potassium. And then you have the same two A and B methods you did for ester. You can use the IUPAC way when R is a benzene ring, you're going to have to. And you drop the IC in the word acid and add OAT, and you have the element name in the front. If R is not a benzene ring, find the longest chain with the carbonyl carbon, name it as an alkane, drop the E and add OATE, and that's how you do it. Now you should know, hint, esters are responsible for the smell of many flowers, or most flowers, and the taste and smell of many fruits and vegetables. If you smell and taste a banana, you're tasting and smelling an ester. Now, how do you make an ester? You react the carboxylic acid with an alcohol, acid catalyst, H+, and you make an ester. Now, listen carefully. The carbon with the hydroxy group in R prime is the carbon this oxygen in the ester is bonded to in R prime. The carbon in the alcohol R prime OH is the same carbon that's bonded to the oxygen here. Now, reactions of esters. If you take an ester and react with acid and water, you'll get back the alcohol and the carboxylic acid you would have used to make that. Now, if you take an ester and react with base, where a base can be a lithium, sodium, or potassium hydroxide in water, you'll get the carboxylate anion of the carboxylic acid, because you're in base, and that carboxylic acid up here forms the carboxylate anion, but you do get the alcohol also, two things. Now, one of my favorite reactions is if you take an ester and react it with not one, but 2 molecules of a Grignard reagent. I didn't put in here, I'll put it now. Where X can be chlorine, bromine, or iodine. Second step, acid and water. Keep your eye on the carbonyl carbon. The R group's still there. Carbonyl becomes an alcohol, and you have not one, but 2 carbon-carbon single bonds you've created to that carbon with the 2 R groups of the Grignard. And this part here becomes this alcohol there. All right, next I talk about amines. Amines are where you have a nitrogen with R groups. Amines can have 3 bonds to it. So primary amine, which I won't ask you what it is, but 1 R group, 3 minus 1, 2 hydrogens. Secondary amine, 2 R groups, 3 bonds, 2 nitrogen. And amines, 3 minus 2, 1 hydrogen. And finally, a tertiary amine, you have 3 R groups, 3 minus 3, 0 hydrogens. Now, I've only asked you to learn the common names for amines, and that is name each R group as the alkyl group it is, put that in the front, and then add the word amine. Now, there's one special amine I'd like you to know. When you have a benzene ring of bonded to nitrogen and 2 hydrogens, that's called aniline. Now, something very near and dear to my heart, quaternary ammonium salts. That's when you have 4 groups on nitrogen, has a positive charge. You have an anion. For this class, the anion will be chloride, bromide, Cl minus, Br minus, or I minus. Now, how do you name quaternary ammonium salts? Name each R group as the alkyl group it is and put that in front. Then add the words ammonium halide. Now, when it's bromine, that halide is called bromide. When it's chloride, it's called chloride. And then when it's iodine, it's iodide. Now, there's also something, I made a mistake here. Dr. White made a mistake. I'll have to correct it tomorrow, maybe I'll get to it. And here, you have an amine salt, and here you have a nitrogen with 1 hydrogen and either 1, 2, or 3 R groups. Remember, R prime and R double prime can be hydrogen, 1, both, or none. And how do you name them? Same as quaternary ammonium salt. You name the R groups. Now, in an amine salt, you'll never have 4 R groups because that's quaternary ammonium salt. But in an amine salt, you'll never have 4 groups. You'll have 1, 2, or 3 R groups you name. And then you do the ammonium halide. Now, how do you make an amine? Well, you can take, this is called alkylation of amines, which I won't ask. You can take a primary alkyl halide ammonia to make, in the presence of base, a primary amine. You can take a primary amine, react with an alkyl halide, and make a secondary amine. And you can take a secondary amine and react with an alkyl halide in the presence of base, and you make a tertiary amine. Now, when you add an R group, the carbon with the halogen is what's bonded to the nitrogen. When you add an R group, the carbon bonded to the nitrogen was the carbon on the halogen. Now, a really neat way to make a primary amine is a nitrile. And remember, it's got 2 pi bonds and 1 sigma bond. And like carbon-carbon triple bond, a carbon-nitrogen triple bond, if you add excess hydrogen to catalyst nickel, platinum, or palladium, you break the 2 pi bonds, and each atom of the triple bond gets 2 hydrogens. You can write it like this or like this, primary amine, either one's right. Now, let's talk about quaternary ammonium salts. And this is a reaction that's really, really near and dear to my heart because it helped make me a lot of money. Paid off for cars, my mortgage, a lot of good things. And it got me to Europe, Canada, Mexico, around the world, except for Asia. I never got there. Shucks. But anyways, tertiary amine, alkyl halide, base. You make a quaternary ammonium salt. Remember, it has to have an anion. For this class, X can be chlorine, bromine, or iodine. Now, an amine salt is made because amines are bases, and they accept a proton from an acid. And this class, I'll use the acid HX, where X is chlorine, bromine, or iodine. This can be a primary, secondary, or tertiary amine. Therefore, R prime and R double prime, one, both, or none, can be hydrogen. And you add a hydrogen to get a charge here. You don't have to show the charges. And you have the anion present. And you don't have to show the actual minus sign there. Next, I talked about amides. And amides is where you have a carbonyl, carbon double bond to oxygen, R group here, nitrogen, R. On the nitrogen, you have R prime and R double prime. And note, both R prime and R double prime can be hydrogen. So you have both of them hydrogen, that'd be NH2, one of them or none. And this is an amide. How do you make an amide? You react a carboxylic acid with an amine, primary or secondary or ammonia. R prime and R double prime can be hydrogen. They're both a hydrogen, that's ammonia, NH3, and you get an amide. Now, once you get an amide, remember R prime and R double prime, one or both or none can be hydrogen, and you react it, and I'll use for this class always hydrochloric acid. You use other acids, I'll stick to that, and water. You break the amide down, you get back the carboxylic acid you would have used to make that amide, but the amine you get, because you're in acid and amines are bases, you form the amine salt. And once again, R prime and R double prime can be hydrogen. And next, you can take an amide and react it with base. And for this class, I use sodium hydroxide and water. And what you get back is the carboxylate anion of the carboxylic acid you would have used to make that amide. This reacts with the base to give this, but you also get the amine that would have been used to make that amide. And here it is. And remember again, R prime and R double prime, one, both, or none can be hydrogen. I talked about heterocyclic compounds, and the only thing you need to know, hint, you need to know what is a heterocyclic compound. That's a ring with carbon atoms and other atoms, such as oxygen or nitrogen. Again, you need to know what is a heterocyclic compound. That's a ring with carbon atoms and other atoms, and those are oxygen or nitrogen. And I've asked you to learn the structure of one heterocyclic compound, that's pyridine. And pyridine is like a benzene ring with one of the carbons replaced with nitrogen. Don't forget the double bonds in there. Or you could also put a circle. Whoa, we're done. Any questions?
No questions.
Yes, no questions. Thank you, Chioma. All right, and thank you for teaching me how to pronounce your beautiful name. All right, it's time to, and I got to open it up first, to go through the amines, amides, and quaternary ammonium salt problem set. Wrong button, right button. All right, does everybody see the amines and amides problem set? Give me a thumbs up if you can see it. Thank you. All right, let's look at the first part, and that give the IUPAC or the common name. I didn't teach you the IUPAC, so you put down the common name. And I see a mistake already on A. That should be N-butylamine, not butylamine. My mistake. Now, name each R group as an alkyl group and add the word amine. And here we have ethyl isopropyl. You could have also put isopropyl ethyl. And this is aniline. Now, I got overboard, cross off D, and you don't need to do that. Now, if we look at E, ooh, what's different? Nitrogen. It's got 1, 2, 3, 4 alkyl groups, and it's got a plus charge and a chloride minus. This is a quaternary ammonium salt. Name each alkyl group in the front: 2-ethyl, 2-methyl, diethyl, dimethyl. Remember, di is 2, tri is 3, then ammonium, and for chlorine minus, it's called chloride. Now, for the amine salt, you do the same thing. And here, notice I only have one R group, N-propyl, then ammonium chloride. Now here, draw the structure. Well, here's ethylamine. Start from the right, go left. Amine, nitrogen. What's on there? Ethyl and T-butyl. Cross off C. I shouldn't have put that down. Cross it off. No, don't do it. All right, next one, because this was a molecule that's really near and dear to my heart. I have you learn it. Ditallow, we show tallow group by R sub T, and dimethyl ammonium chloride, 2R sub T, 2-methyl plus charge, Cl minus. You don't want to put the charges, that's okay. Cross off E, and that's that. Now, if we look at A, what do we have? Ammonia plus carbon with a halogen, alkyl halide, make a primary amine. What's our methyl? If we look at B, we have a primary amine, nitrogen with an R group. That R is methyl. Our prime is isopropyl. I didn't put down here, bad Dr. White. And that is that you have X can be chlorine, bromine, or iodine. And what happens? You get a secondary amine. R is methyl, R prime isopropyl. The carbon with the halogen is bonded to nitrogen, and that's what you get. Remember, placement is very important. Next, and this is really near and dear to my heart, because this reaction helped pay my salary at one company. Take a tertiary amine, methyl ditalloamine, reacted with carbon with a halogen, alkyl halide, tertiary amine, alkyl halide. You make a quaternary ammonium salt. One way to write it is this way: ditallow, dimethyl, ammonium chloride. And for many, many years, that was the only molecule that was a fabric softener. Don't forget, quaternary ammonium salts are used as fabric softener and antimicrobial compounds. Example, like my mouthwash. That keeps my gums nice and healthy. Now, if we look at D or E, what do we have? Primary amine, or here's secondary amine, HX, X can be chlorine, bromine, or iodine, and you have a proton transfer to make an amine salt, which is what I did here, and I did here. Now, E, cross off. G, I mean. I think I need glasses. G. Now, let's move on. If we look at H, we're reacting something with excess hydrogen, meaning you have all the hydrogen in the world to react with anything hydrogen will react with, and second, also with a nickel catalyst. And what do we have? Triple bond, 2 pi bonds, hydrogen and catalyst. I don't have it here, but a catalyst can be nickel, platinum, or palladium. You break the 2 pi bonds in each atom of the triple bond. Carbon nitrogen triple bond gets 2 hydrogens. Now, I wrote it this way. You could have also written it. Let me open my whiteboard. Let me go back and peek how many carbons. And that was, okay, 3. And you could have written it this way. On the problem set, I have it, these 2 hydrogens I bring onto the carbon, these 2 hydrogens I bring onto the nitrogen, and the other way to write it, which you should be familiar with, is this. Either one would be correct on my test. All right, now if you look at I, benzene ring isn't going to be hydrogenated, but triple bond will, and this is the product you get. Now let's move on to K and L and also M. What do we have? If we look at K, carboxylic acid and a primary amine. Remember, carboxylic acid and a primary secondary amine or ammonia, our prime and our double prime can be hydrogen, both, one, or none. In this case, one of them is. And you get this amide. Now here in L, got a benzene ring that's not going to react with ammonia, but this carboxylic acid will, same reaction. Now our prime and our double prime are hydrogen, ammonia, and you get this amide. And here again, same thing. Now our prime and our double prime are methyl. This is R, you get this amide. I did it again. Well, I got a lot of them there. Now, if we look at O or P, what do we have? We have in both cases an amide. Remember, R prime and R double prime, one or both can be hydrogen, HCl and water. You get back the carboxylic acid you would have used to make that amide, plus the amine salt of the amine you would have used to make that amide. And in this case, our prime and our double prime are hydrogens. So notice you have 2 here, add 2 more, and H4, and here chloride, R here is methyl. Here, our prime is methyl, our double prime is hydrogen, HCl water, R is benzene ring. You get back this carboxylic acid. And again, remember, you get this amine salt. R prime is methyl. R double prime is hydrogen, which you can write either of these ways. Now, in the presence of base, you can have here a amide reacting with base and water. And where's the general reaction? It didn't put, here it is. I couldn't see it. Amide, sodium hydroxide and water, get back the carboxylate anion, the carboxylic acid would have used to make that amide, plus the amine you would have used to make that amide. And this one, what's our benzene ring? Don't put the carboxylic acid there. I'll mark it wrong because in the presence of base, this reacts acid-base. But you get this amine. And same thing there. Now, I have a couple of synthesis problems. How do you make this amine? There are two different ways. Remember the secondary amine, primary amine plus an alkyl halide base. You form it. I call the methyl group R and the ethyl group R prime. And that would be the top, or I could switch it. And since I don't show you a halogen, you can use any of the three, bromine, chlorine, or iodine. Now, let's look at here, B, how to make a quaternary ammonium salt for our groups with a charge and a halogen anion, tertiary amine, alkyl halide. The arrow fell off. The presence of base, you get a quaternary ammonium salt. Boy, did I mess up on this one. And you can do it two ways, how you sparse dimethyl or R and R prime. One, the ethyl is R double prime, and the other ethyl is triple prime. You get the top one, or do the other way, you get the bottom one. Now, let's look at C. If you have a primary amine and you're reacting something with hydrogen nickel, what do you start with? A nitrile. And remember, one of the carbons in this chain here is the nitrile carbon, carbon double, triple bond to nitrogen. And with that, this is my R group, and that's my nitrile. And here I have the synthesis. You take something, react with acid and water to get a carboxylic acid and an amine salt. What do you need to start with? An amide. And here's R to the carbonyl. On the nitrogen, you have R prime and R double prime. Remember, R prime 1 or R double prime 1 or both can be hydrogen or not, or all of them. In this case, 1 is hydrogen and R prime is N-propyl. Therefore, this is the amide you get. And finally, in base, you react something with base. What do you get? Well, here, what's different? Carboxylate anion and an amine. What do? You start with an amide when you react with base and water. And what's R? Ethyl. What's R prime? Ethyl. Remember, R prime and R double prime can be hydrogen. In this case, 1 is. So here's the amide. R is ethyl, carbonyl, nitrogen with a hydrogen and an ethyl group. I'm done. I did both the review and the problem set. And don't forget, I will be posting this later today. So if I went a little too fast, you can go back and watch it again. If I look at the clock, it's time for a break. And why don't you come back at 2:55 and we'll continue. We'll start new stuff that won't be on test 3, but will be on test number 4. And don't forget, this Saturday, I'll have my special, I'll put it out in an email, special before test number 3, office hour. And with that, I'll see you at 2:55. time to get going. Oh, attendance has doubled. All right, let's get going. And for those who came in late, and you can watch the video, which I'll post later today. I went through the test number 3 review, because test number 3 will be this Monday after class. And then I went through the extra credit project. Watch it, because 10 bonus points if you do it right, and that will never hurt your grade. I'll help it a lot. And then I went through the amines, quaternary ammonium salts, and amides problem set. So now I got to open up some stuff, and I can close this. Let me do one thing to be safe. Let's do an experiment. I'll be with you in a minute. I think I found our problem why I get things burping, because the system opens up a ton of temporary files, which I just ran a program called CCleaner. And let me just open up one other thing. Hopefully we're good for the rest of the day. All right, everybody see on their screen synthetic polymers. Thumbs up, people, help me out. Uh-oh. Not on your, oh, thank you, Shelma. All right, now, this new chapter will not be on test number 3. It will be on test number 4, Now, this deals with synthetic polymers. Before I start, I should tell you, I personally could give a 2-semester graduate level course on synthetic polymers. Yeah, that much. However, I'm going to do everything. I'll teach you everything you need to know for this course in less than 40 minutes. Really? This will just give you a good overview of what is a synthetic polymer. Now, remember, the word synthetic means to make, and polymers, that means something that chemists make as opposed to Mother Nature. Now, you should know, what is a polymer? Ooh, where's my special message to my students time? I haven't done this in a while. And you should know, what is a polymer? And a polymer is a macromolecule. Macro means big, and I mean big, molecule built by repetitive linking of smaller units called monomers. Now, the word poly means many, and monomer, unit, says many units made of monomers, single units. The best way to think of this is, think of a long, I mean long freight train made up of the same boxcar or 2 different boxcars, or a boxcar and a tank wagon, or tank car, I mean. And it's long, I mean long, I like that. And that's what a polymer is. A polymer is a macromolecule, huge molecule, built by repeating units of smaller units called monomers. So that's a polymer. Now, when we talk about polymers, and hint switches on big time now, this is another one hint, you should know this. There are two types of polymers, and this is a way of classifying polymers. One is by chemistry, the other is by an important physical property. Let's talk about the two types of polymers based on chemistry. And they are an addition polymer and condensation polymer. So there are two types of polymers, addition polymer, and when we talk about based on chemistry, or condensation polymer. Oop, I'm missing a slide. I've got to get to work. Well, first of all, an addition polymer is made with one type of monomer. And it's like the same freight car repeating over and over and over and over again. And we're talking long, like 1,000,000 carbons. Wow, that's big. And examples of this that you should know, saran wrap or the plastic wrap in your kitchen is an addition polymer. Another example that you should know, at least one example of an addition polymer, which is a polymer made with one type of monomer, is rubber. An example of that would be rubber car tires, your car tires. The rubber in your car tire is an addition polymer. It's made of this one unit that's connected together over and over and over again. That unit is called isoprene. So an addition polymer is made with one type of monomer. You should know this. And examples you should know, well, one is saran wrap, another is the rubber car tires. And there are others, but these are two you should remember, one of them at least. Now, the other type is condensation polymer. And condensation condense, bring two things together, is made with two or more types of monomers. So if you have a condensation polymer, it's made of two or more different monomers. And I'll talk a little bit later about the chemistry, but here, examples that you should know of items in our daily life, just like up here I did. One is plastic bottles. like my water bottle here, which I'm going to take some, not the bottle, the water. And the plastic here in my water bottle is a condensation. It's called a polyester. It's made with two different types of monomers. And if you go to the supermarket and buy bottles of pop, that's the stuff that's non-alcoholic, carbonated. I'm from the Chicagoland area, and we call that pop, not soda. That's also a condensation. Now, another one is nylon. And if you have a nylon jacket, which would be an item, and I do have some older from companies as promotions, those are, the nylon is a condensation polymer. Now, nylon was originally made in World War II, developed to replace silken parachutes. And the story goes, near the end of the World War II, or just afterward, silk had been put on, I forgot the right word. It was used exclusively only for parachutes, and therefore women at that time had stockings made of silk. Well, they couldn't get them. And turned out this guy who invented it, story, I don't know if it's true or not, but I've heard it, I've read it actually. And that is, after the war, while you couldn't get silk for stockings, his wife or girlfriend was upset. He realized, this nylon I can make into stockings. And he did. And that's why women's stockings after that were called nylons. And now they're used in, and again, I don't have any, but pantyhose are made of nylon, a condensation polymer. So you should know addition polymer made with one type of monomer. Example, saran wrap and rubber car tires. You should know condensation polymer made with two or more different types of monomers. Let me move us over so you can see that. And examples that plastic water bottles or nylon jacket or anything else, nylon articles. Now, the other way of classifying polymers is by a key physical property. And that is, once something, a polymer shaped like a bottle is formed, can it be reheated and made into something else, a new shape, or it can't. And those two types are called thermoplastic and thermoset. And you should know this. What's the thermoplastic? That's a polymer once formed in a shape can be reheated to form new shapes. So in other words, I can recycle this bottle. This, if I take the label off, which is, I guess, a polymer or paper, I don't know which, I can take this plastic, heat it up, it will melt, and I can mold it into another bottle or other things. Now, examples of this is the polyester, which I should really put this way. Another example would be saran wrap. That's what polyethylene is. Or that kitchen wrap. I don't buy saran wrap. I get it from Costco. And nylon, like nylon jacket, those you can all melt and reshape. And therefore, they're called the thermoplastic. Now, the other type is called the thermoset. And the thermoset, once it's formed, it can't be reheated to form a new shape, which means it's can't be recycled. I don't have it here, but example would be a car tire, rubber car tire, or phenolic resins. Your buttons on your shirts, unless they're metal or other places you have buttons, are made with a compound called phenolic resins. My last patent dealt with phenolic resins. I also have patents in what's called urethanes. And we'll talk more about urethanes this chapter. But if you like the way it feels when you sit down in your car on the seat or in a sofa, you're sitting on what's called a urethane foam. And those can't be recycled, reshaped, and you should know that. Now, switches off here. I just wanted to quickly say addition polymers are made by a reaction which I haven't talked about called free radical polymerization. And a radical is in a very, very, very reactive species. And this is where the same monomer reacts with itself. And free radicals, you have what's called a radical initiator. You form a radical, sometimes they do it like this. This attacks the double bond to form a new radical, and it keeps on attacking more of this same molecule. And polymer chemistry, on the double bond, some group here is called L. And notice this is repeating over and over again. And this end is the order of 500,000, I mean big, to 1.5 million, if I can spell it right. Let's try that again. It's huge, and that's how it does it. Now, switches off. Let's take a quick look at some key monomers and the products they make. If L is a hydrogen, this is called ethylene. It makes polyethylene. That's your saran wrap. When L is a methyl, you make polypropylene. Poly means many. How many of you have ever seen the plastic bubbles on things like a thumb drive or other things? It's hard that there's a plastic bubble with the thing underneath it, and you try and get it open with scissors, knives, and it's hard to break into. That's polypropylene. Now, how many of you have ever seen the white insulated cups or the bigger cheap insulated foam coolers? Those are made when L is a benzene ring and you get polystyrene. Now I have some others. One I do want to talk about, when L is a chlorine, this is called vinyl chloride. That's a common name. The IUPAC would be chloroethene. Nobody uses that. It's called vinyl chloride. And when you put a lot of those together in polymerization, we have a product called polyvinyl chloride. Again, switches off here, but it's interesting. And it's also known as PVC. That's the white pipes underneath your sink in your bathroom or your kitchen are made of polyvinyl chloride. All right, now, switches on. Turns out certain polymers, think of long strings, each of maybe 1 million carbons. But in the molecule, you have a lot of those long strings. Now, before someone came up with the following invention and concept, you could pull it this way and it would be strong, but if you pulled it this way, it fell apart. Well, someone, who I'll tell you who, commercialized the first, a number of chemists were working on this, but the person I'll tell you was the first one to perfect it to be used as make commercial products. And we're talking about cross-linking. Let's assume I have these 3 polymers or 4 polymer strands or molecules. If I go this way, it's pretty rigid, it's strong. But if I pull it this way, it falls apart. Well, if I chemical bond this to this, and then this to this, and this to this with cross-linking, that's called cross-linking. You link between the different strands. Now pulling this way, it's pretty hard. You've gained a lot of strength, important physical properties. You may make it more rigid and more useful. And this is called cross-linking. You should know that. Now, sad story. Who was the one who first came up with this back in the early 1800s and commercialized it first and got a patent? A gentleman named Goodyear. Have you ever heard of the name Goodyear? You're right, tires. Well, it turned out there was never a Goodyear in the Goodyear Tire Company. What? Well, sad story is the Goodyear, and I can't remember his first name, who came up with this commercialized cross-linking with rubber. It's called vulcanization to make rubber strong like it is. You look at rubber without cross-linking, it's this gooey mess. It's not worth use. It's not that useful. You cross-link it and you can make things like your car tires. Now, the sad part was Goodyear was an alcoholic, and 2 businessmen who are very savvy saw what he did and learned about it. This is going to be worth a lot of money. And they went to him. And at the time, I don't know, they gave him $20,000, which today would be $1 million or $2 million or whatever, and said, sell us your patent rights and sell us the right to use your name. Because a lot of people knew about Goodyear. And he did it. And they went and created a Goodyear rubber tire company. And you know the rest of the history there. What you don't know is Goodyear died with not too much money because he drank it all away. Sad. Now, condensation polymer, switch is still off, is made when you bring 2 different functional groups together and you form a new functional group. Just like if you have making an ester, I hope you know this reaction for Monday, you make an ester. Well, what if you had a molecule with 2 carboxylic acids and 2 alcohols in it or more? Now you can make a polymer. Or you can, instead of a carboxylic acid with 2 carboxylic acids, you have an amine with 2 different amine groups in it. You can also make a polymer that's got amide functions holding things together. And you can make polyesters like my water bottle, polyamides like nylon jacket or whatever. Now, there are other groups you can create, and that's the urethane foam from urethane reaction, I'll show you briefly, or phenol reacting with formaldehyde, or even epoxy functions, which I'm not going to show. Now, polyester, again, switches off now, is when you take a carboxylic acid, di-2, and a diol, OL alcohol, and you get this ester. Now, at this end, I still have more alcohol that can react with more of this. At this end, I have more of the carboxylic acid that can react more with this, and it keeps on repeating and repeating and repeating like the Energizer Bunny. And it makes this. Now, you can do the same with an amide. And here's an example, switches off. If I take, this is paraphenylene diamine, 2 amine groups. This is called an acid chloride. We learned about it for Friedel-Crafts acylation, but this acts like a super powerful carboxylic acid. So you can make amides with this real quick. And you have base because you're generating hydrochloric acid, which you don't want around. And you get this polymer where N is on the order of about 1 million. And this polymer has a trade name, Kevlar. When you make fibers, cloth of Kevlar, and you layer them on top of each other, it's strong. Why? Because you got those benzene rings, which are rigid. And it's so strong, sheets of Kevlar are sewed together to make bulletproof vests for people like policemen. Now, polyurethanes uses this functional group called the isocyanate function, which very quickly reacts with an alcohol in the following reaction. Oh, by the way, I make a mistake here. There should be a hydrogen right here. Oops. And this is function, carbonyl, oxygen with an R group, nitrogen with an R group. They can be the same or different. Why I have R prime. It's called the urethane. And I only have about 6, 7 patents in urethane technology. And so I know it quite well. Now, the formaldehyde phenol, I'm just going to say it's used to make different resins, glues. And I worked in this area in my last patent, dealt with phenol formaldehyde polymers. Wow, everything you wanted to know about polymers in a quick amount of time, less than 40 minutes. But I'll go through this again. And by the way, for those who came in late, quick announcement this Saturday morning, and I'll send out an email at 9 a.m. and I'll also send out an email, the link, because it won't be the same as my office hour. I will be on Zoom if anybody needs help for test number 3 or needs practice, come on by and I'll do it. All right. Well, we're moving along, which is what we do with that chapter. Let me just check something, make sure I'm on track. Yeah, it looks like I'm on track. So I better get to work, which means I got to open up a new file. Again, this is material for test, not 3. Let me open it first. But test number 4. And let's talk about lipids and detergents. And in this chapter, I'm going to talk about things you wouldn't think about. You'd learn, like how does soap get your hands clean, and a whole lot of other neat things. And this is an area I also worked in the chemical industry. Now, what's a lipid? And I'll turn the switch, click off. That's constituents, some chemicals of plants or water that are characterized by their solubility. They're insoluble in water, but soluble in non-polar organic things like ether, or gasoline, or hexane. And that's called a lipid. Now, switch is off, but let's go to the next slide. Oh, it's Subtle Thursday. And there are 2 types of lipids that you should know. The first one is called the saponifiable lipid. And what is a saponifiable lipid? Now I have here, can be hydrolyzed under alkaline conditions to yield salts of fatty acids. And another way of thinking of it is they react with base, which is alkaline, and water to make carboxylate anions, which is what this is. So, saponifiable lipid reacts with base and water to form carboxylate anions. Now, the other type of lipid you should know, remember, know this, is non-saponifiable lipids. And they do not undergo hydrolysis reaction in alkaline solutions. Another way, let's see if I can spell better. So non-saponifiable lipids do not react with base and water, no reaction. Saponifiable lipids do react with base and water to give carboxylate anions. Now, what are saponifiable lipids? Remember, this is for test 4, not test on Monday. And we call saponifiable lipids fats and oils. And you've also heard them called triglycerides, or sometimes, which you probably, triesters of glycerol. And a number of years ago, when I went to new doctor at this new group I started going to, I had my physical and a blood test and everything. And he called me and I got a phone call from his office. Doctor needs to talk to you soon. I said, oh, really? And I'm wondering what's wrong. And great doctor, unfortunately, I had to retire early because he had back problems. And the new doctor I have, the same group, is also great. But he called me in and I loved him because he was always straight with me and, you know, didn't sugarcoat things. Said, I looked at your blood work and physical. I've got to talk to you. And that's why I wanted you in. I said, what's wrong? Said, one of the things is your triglycerides is too high. And he showed me something on the screen on the computer, said, you're in the 95 percentile. What's that mean? Said, if you don't get that down and a few other things under control, you're going to be dead in 5 years or less. What? It woke me up like that. And he helped me get that down, which it is. And that was more than 5 years ago, a lot more. And good news, I'm still alive, which is good to me. I hope you like it too. So, but that's a triglyceride. And these are the other way of knowing it is fats and oils. Now, what's the structure of a triglyceride? Now, before I show you the structure, chemists who work in this area are called oil chemists. And it's not oil from the ground, that they're called petroleum chemists, but oil chemists work with animal fats and vegetable oils. And a triglyceride, now normally synthetic organic chemists write their ester this way. Oil chemists, which I have been, write their esters this way. and they're both esters. We put the R prime a little differently and writes this backwards. And now let's look at the structure of triglycerides that you should know. And each one of these is an ester. And this is a structure of all fats and oils. Well, and I'll talk more about fats and oils. And the only difference is what's R prime, and R double prime. Now, if you notice right here, I have a carbon, and I'll write it like this: oxygen, carbonyl, and either R prime. I'll write it this way, this group. This is ester number 1. If I look here, carbon, oxygen, carbonyl, R group, ester number 2. And here, carbon, oxygen, carbonyl, R group, ester 3. So triglyceride has not 1, not 2, but 3 esters. Sometimes it's called triester glycerol, but you probably never heard that. I have, because I worked in this industry. Now, you should know what is a fat. And a fat is a triglyceride that's a solid or semi-solid at room temperature. Now, in case you're wondering, room temperature is 25 degrees C. You don't have to put that out. But a fat is a solid or semi-solid at room temperature. What's a semi-solid? How many of you have ever seen butter that's been out for a while? If you touch it with a knife or your finger, it's sort of smushy. Well, that's the scientific term, but it still holds its shape. Or if you want, and you don't have to do this, if you had some mayonnaise in the refrigerator, you stick your finger in there, somewhat solid, but your finger goes right in. Or you can use a spoon or knife. And that's a semi-solid. Now, what is an oil? And you should know, an oil is a triglyceride that's a liquid at room temperature. And if you look at vegetable oil, olive oil, at room temperature, they're all liquids. What would be an example of a fat? Have you ever made bacon? Or if you don't like pork, hamburgers. Hopefully, if you're not a vegan, vegetarian, you've done one of those two. And if you fry hamburgers, ground beef in a frying pan, afterward, you'll see a lot of liquid in there. If you make bacon in the same type of frying pan, after you take the bacon out, after you fried it, you'll see a liquid in there. Now, if you let it cool down, because it was hot because you heated it to room temperature, that liquid of fat becomes a solid or semi-solid. So fat, triglyceride, that's a solid or semi-solid at room temperature. Oil, triglyceride, that's a liquid at room temperature. Hint, you should know that. It says 4. Now, let's look at some reactions of fats and oils with acid and base. Guess what? You already know these reactions. Nothing new for now. As I said the other day, I've gone through all the new general reactions, but we're going to take those out into the real world. So let's do a general triglyceride. And remember, if I'm going too fast, you can always come back and look at the video. And this is a fat or oil. Now let's react it with acid and water. what happens? Well, hopefully you remember for test number 3, you've learned for Monday, if I have an ester, now I'm going to write it backwards, and react it with acid and water, I'll get the alcohol I would have used to make that ester plus the carboxylic acid. And again, fats and or oil chemists write it backwards like this. So we have 3 esters, 1, 2, 3. Let's do ester number 1. What's our CH2? I'll have an OH group, but it will be bonded to something else, this carbon, because you break carbon-carbon single bonds? No. Now, this part will give this carboxylic acid. And the R group here is this R. Ester number 2. I'll get this carbon, which is R, and it will become an alcohol. It's still bonded to carbon here because you don't break carbon-carbon single bonds. This part will give this carboxylic acid. And notice here, that's R prime. So I'll do R prime. And finally, ester number 3, this carbon, CH2, that's my R group, and I'll have an OH group. This molecule right here, we talked about it in alcohols briefly, is called glycerin. If I can spell it. And we'll also from here, this ester, get this carboxylic acid. So nothing new, but when you take acid and water, react, and this is a fat or oil, any fat or oil, this is what you get. Now, I don't know if I've done it that much this semester, but when I was a college student, well, that was a long time ago, if something was really important in my notes, I'd put a couple of stars. If it was really important, I put the stars, an IMP, and an arrow, and underline it, and I know I better know that for the test. And this is that sort of thing. Why? Where do you get acid, HCl in your stomach? Where do you get water? Well, if you've been drinking water like you're supposed to, my doctor says you got to drink water to stay healthy, which I do. This is the reaction how your body breaks down fats or oils in your stomach, and I think it's your small or large intestine. One of the miracles of life that just always makes me wonder, wow, is you and I have cells in our body that make hydrochloric acid. And that's the acid in the stomach, that's the H plus. And your body makes these acids, carboxylic acids, plus glycerin. I also worked for a company that made glycerin fatty acids, or the carboxylic acids, I'll teach you later, from fats and oils are called shortened to fatty acids, the tune of about 2 to 3 million pounds a week. Yep, of each. So this is a reaction you should know. Triglyceride, 3 esters, acid and water. You've learned this reaction for test 3, I hope. And that's ester, acid, water. Get back to the alcohol and the carboxylic acid you would have used to make that ester. Now I'm going to stick this right now to one base, make your life a little easy. Don't tell anybody, I'm being nice. Shh. Let's look at this reaction. What's the general reaction? Well, here I have 1, 2, 3 esters. I'm reacting with base and water. And I'll write my ester backwards like oil chemists do. Remember, it's not oil like in from the ground, it's fats and oils. I should mention a very large, which for a long time until I got out of this industry and worked for another one, I was a member of, and that's the American Oil Chemists Society. And that oil is not petroleum because there's a separate one called petroleum chemists. That's fats and oils. And their headquarters, are you ready for this? Is in Champaign, Urbana. And here, hopefully you learned this for test number 3 coming up next Monday. If I take an ester and react with base, sodium hydroxide and water, I'll get back the alcohol I would have used to make that ester, but because I'm in base, I don't get the carboxylic acid, I get the carboxylate anion of that ester or carboxylic acid. So if we look at ester number 1, R is this, and it'll have this alcohol, but it's still bonded to something else. I'll get this carboxylate anion. By the way, this is called saponification of an ester because the carboxylate anions you get are soaps, and I'll teach you that later on. Second ester, I'll get this alcohol plus what's my R group on the carbonyl, R prime. I'll get this carboxylate anion. And finally, the third ester, I'll get this alcohol plus this carboxylate anion. And depending what fat or oil you start with, what's our prime and our double prime. So once again, you get glycerin, but you get the carboxylate anions of the carboxylic acid you would have used to make that ester, in this case, the fat or oil. And if I look where we are, let me go back to my slides. And I can tell you which the carboxylic acid that you get when you react acid and base, acid and water with a fat or oil, this is called a fatty acid, which is short for fatty carboxylic acid. They're always even number. Mother Nature never did odd, and there's no branching. It goes from 12 to 26 carbons. And with that, let's take a 5-minute break. I'll see you at 3:50, and we'll continue on. And then we'll also do the lab for today. So I'll see you in 5. Looking good. Let's get going. All right, I was talking about fats and oils. And fatty acids, oops, hold on. I always forget to do this sometimes. All right, everybody see fatty acids on your screens? Give me a thumbs up if you can. Thank you, Jimmy. All right, thank you, Chioma. All right, now, fatty acids are carboxylic acids where the carbonyl carbon, and Jimmy too, thank you, everybody who did that for us. And you have the carbons in R and the carbonyl carbon are always total even numbers. It goes from 12 to 26 carbons. And most common are 16 and 18, and some smaller ones too. Now, I'm going to ask you, first of all, there are two types of fatty acids, which are fatty carboxylic acids. One is a saturated fatty acid. Oops, I did something I didn't realize. I did. Working in the industry, FA stands for fatty acids. Now, what's a saturated fatty acid? If you remember, a long time ago, beginning of the semester, we talked about saturated hydrocarbons. And those are molecules with only carbon-carbon single bonds. Well, saturated fatty acid is a fatty acid where the carbon chain in which all carbon-carbon bonds are single bonds. If you put down has all single bonds, I'll mark it wrong. You should know this. Why? Because you got a carbonyl, that's the carbon oxygen. And you should know an example. And let me write it on my whiteboard. Named after me, not really. This is probably one of the widely used saturated fatty acids, and you should know the structure. Now, unlike in the past, I'm going to use the parentheses to show a repeating unit because I'm not going to spend all your time watching me write 16 CH2s. This is the structure of stearic acid. On a test 4, if I write, draw the structure of stearic acid, there it is. If I ask what's the name of that compound, the common name is stearic acid. Nobody ever calls it hexadecanoic acid. They don't. It's stearic acid. Now, I worked for a company, Unichem Chemical, on the south side of Chicago for a number of years, where I was the laboratory manager, in charge of quality control for the plant there, and also the research in the United States at that site. And we made millions of pounds a week of stearic acid. Now, stearic acid is a white solid, and it's pretty harmless. You can eat it, I wouldn't, but just so you know, what's some uses of stearic acid? Well, 50% of the weight of good candles, high quality candles, is stearic acid. The other is paraffin wax. So that's one use. Now, another one is with a company that's now a division of another company, but when it was, before it got bought out, it was called Binney Smith. Have any of you ever heard of Binney Smith? Give me a thumbs up. No, and I knew that. But what's the product they made and still do? Crayola crayons. And half the weight of a Crayola crayon is stearic acid. The other, essentially paraffin wax, like a candle, but it has some coloring in it, a pigment. So when you draw on a piece of paper, it's colored. And is it toxic? No. If you ever heard stories about kids or dogs or other animals eating Crayola crayons, it has a very colorful ending. So, but anyways, and one time I got a call from the president of our company, this Unichem, got to be on a plane tomorrow and go to Benny Smith. They used to buy millions of pounds of stearic acid. And this is when they made the crayons in the United States. I don't think they do anymore. And it was outside of Pittsburgh. And a salesman there picked me up and took me to Benny Smith. They had a problem that they said, it's your chemical, solve it. And that happens a lot of times in the chemical industry. Somebody buys something from you, they've got a problem, they say, you're causing it, solve it. And I went there and I saw how they make crayons. Well, it was amazing. And I found out what the problem was. I can't tell you because it's a trade secret. But I learned how crayons were made firsthand, saw it, and it was amazing. I mean, really high speed, like zoom. So stearic acid, saturated fatty acid. Notice here in the R group, only carbon-carbon single bonds. All right, next. Let's talk about monounsaturated fatty acids. Now, mono means one. Remember long ago, we learned about unsaturated hydrocarbons, and that's a hydrocarbon molecule with only carbon, nitrogen atoms that has at least one double or triple bond. However, Mother Nature never, ever made anything with a triple bond in it. That's something organic chemists created. So what's a monounsaturated fatty acid? Mono means one, unsaturated. It's a fatty acid having a carbon chain in which one or more, I don't know, I should have more than one, or mono would be one carbon-carbon double bonds present. And the name of that is oleic acid. And the company I work for, we made oleic acid. And let me show you the structure of oleic acid. In fact, when I was there, I developed 2 new quality types of oleic acid that sold quite well. And you should know the structure of oleic acid. And this is oleic acid. Notice it has a double bond, and this is at carbon number 9. We show that C9. Remember, the carbonyl carbon is 1 plus 7 is 8. That makes this one 9. This double bond can be cis or trans. We'll talk more about that later in this chapter. And this is oleic acid. It's a liquid at room temperature. And by the way, your body makes both from acid hydrolysis of fats and oils. Now, you learn for esters, take the name of the acid, drop the IC and the word acid and add OAT. Or add ATE, I'm sorry. So if you see something that says stearate or oleate, that's an ester made from stearic or oleic acid. And if you look at a lot of your personal care products, like your skin creams or your hair conditioners, you'll see words like oleate, stearate. There are others called palmitate that are molecules, esters, that are made from fatty acids, which come from fats and oils. Now, I work for a company that made the fatty acids, and we sold to companies like Procter & Gamble, Neutrogena, and other companies that made personal care products and lotions. And you should know, let's go back. On a test, if I ask, draw the structure of oleic acid, you should know this is the structure. And it's pretty simple. Carbonyl, 7 CH2s, double bond, 7 CH2s, methyl group, 18 carbons. Notice both stearic and oleic acid have 18 carbons. Oleic has a double bond. Stearic doesn't. Now, switches off, you can have polyunsaturated fatty acids where you have more than one double bond, 2 or more. Example 2 would be linolenic. Yes, I worked in this industry. I know this stuff. All right, now, the fatty acids can be cis or trans. As you saw, double bond. And an oleic acid, if you have a fat or oil or fatty acid where the hydrogens on double bond are same side, it's a cis fatty acid. If they're opposite, it's a trans fatty acid. Now, let's think about this. And this is something you should know for your personal life. And in your stomach, there's acid and water. If you eat a fat or oil, you'll make glycerin. I'm going to do this fast because I've already done this. Plus different fatty acids. And one of those can be oleic. Now, think about this. If the R group and the fatty acid can be cis or trans, that means the R group and the fat can be cis or trans. And how many of you have heard medical science has told us trans fats are bad for us? Trans fats are bad for us. And then a number of years ago, they came out with that, and cis fats are better. And what that means is the double bond R or R prime or R double prime in a fat or oil, which makes these fatty acids, which has that double bond. When that's trans, it's bad for you. When cis, it's better. Why? I really don't know. I'm an organic chemist, not a medical doctor, but I've been told that and read that, and I believe that. Now, since I worked in this industry, I'm going to share something with you. There are different types of fats and oils. You should know that beef fat is called tallow. And BFT stands for a type of tallow, bleachable fancy tallow. But you should know beef fat is tallow. You should also know pig's fat is called yellow or white grease. Again, you should know beef fat is tallow, and pig's fat in the chemical industry is not called lard, which is in you were using the book, which when I first saw it, I said, oh, whoever wrote this book, well, I know who did. I knew Harold Hart, the original author. If we were using a book, which we're not, never worked in the chemical industry like I have, but we call that yellow and white grease. Now, pig's fat and beef fat, tallow, and white and yellow grease are very important chemicals that are used to make many, many things you use in your daily life. How important? Well, guess what? If you know where to look, and I do, you can see the weekly cost price for tallow, yellow grease, white grease. Where? The Wall Street Journal. Yep. And also another magazine, which I got for people in the oil, fats and oils industry, called CMR, Chemical Marketing Reporter. And every week they had the price of beef fat, tallow, and yellow grease, white grease, two different types of pig's fat. Let's do something real quick. Here's another company, but this is price per ton, and here's per kilogram in 2019, but let's see how much they show you. And they only go through 20, and it's come down. And here they have different types of fats from different animals. Mainly, I've never seen sheep or goat's fat, but tallow, and you can't see it, but here's tallow. It's come down from, I remember 2011 was super high, and you paid for that. But anyways, that's a very important chemical, both of those. Now, let's go back to this chart. I'm not going to ask you, I think you're familiar with coconut oil, soybean oil, you might be corn oil. I hope you all are familiar with olive oil. Now, how many of you are familiar with an oil that's used widely, and especially some of the poorer countries in the world, called rapeseed oil? Are you familiar with that? Probably not. Here's why. Rapeseed, which is pressed the seeds to make the oil, just like olive oil, the olives are pressed to get the oil out of them. Rapeseed oil, one of the big places it's grown is Canada. And they were trying to get Americans to buy this, they wouldn't. And someone very smart in a marketing group in Canada who represented the growers and manufacturers of this rapeseed oil came up with a great idea. And the great idea was, and this won't be on the test, but the great idea was, we're in Canada, we're selling oil, and Americans are not going to buy it when it's labeled rapeseed oil. Let's call it Canada Oil Canola Oil. And if you go to any supermarket around here, at least where I live, you can buy canola oil. And that's made from rapeseed. Everywhere else in the world, it's called rapeseed oil, but American housewives and their husbands wouldn't buy it until it was renamed canola oil. And it's good stuff. Now, switches off, but here's some of the important ones. Saturated, stearic, palmitic. I've worked with all these. Lauric, unsaturated, oleic, and here they have cis, it can be trans. Here they have cis-cis, it can be trans or cis for those two double bonds. And this will not be on the test, other than you should know the structure of stearic oleic. Now, from your book, if you look here, you have saturated fats, which come from saturated, or acids come from saturated fats, and unsaturated with a double bond. Now, medical science has said unsaturated fats and oils, mainly oils, are much healthier than saturated fats and oils. And if you look at, and they have tallow, and also they have a lard that's really yellow grease, white grease, about 50% is saturated and about 50% is unsaturated. And that means it's going to be a solid or semi-solid, and it can help clog up your heart. Now, the vegetable oils, look at olive oil, it's almost 90% on this table, unsaturated fatty acids, which means the R group on the oil is unsaturated, which means the liquid at room temperature, and it's much healthier for you. You know something? This would be a good time to start the lab. So let's start the lab. I got to open the lab first. All right, everybody see on their screen, like dissolves like. Thumbs up, people, if you see it. Thank you, Jimmy. All right, now, this lab deals with the concept like dissolves like. And when you did this, it's important because like dissolves like is what's called the rule of thumb. I think it's on this thumb. Can you see it? A bad joke, Dr. White. Yeah. But anyways, a rule of thumb is something that's mostly true. A law in chemistry and other things too, but in chemistry is always true. But a rule of thumb, most of the time it's true, but there are exceptions. So that's why you can't call it a law. And this lab deals with like dissolve like. And like dissolve like describes that polar substances are soluble in other polar substances, like dissolves like. And nonpolar substances are soluble in nonpolar substances. And when you mix polar and nonpolar together, they're not soluble. Now, in this lab and in this world, our planet, water is the most polar substance, period. Hexane, which is like gasoline, but it's smaller chain length, is nonpolar. So we have water is polar, hexane is nonpolar. And the nice thing about this lab is you're going to investigate, if we were face-to-face in the lab, I'll show you what you'd be doing. You'd investigate are certain compounds and things you use in your daily life, polar or nonpolar. And how do we do that? You test and see if it's soluble in water, it's polar. If it's soluble in hexane, it's nonpolar. Now, because it's a rule of thumb, see it's on this thumb today, not this one, it's not always true. So once in a rare occurrence of testing, you'll find a molecule that's soluble in both polar and nonpolar. Now, this concept of like dissolves like, we're going to come back to later in the lipids chapter and detergents, because it's the key principle how soap works, detergent works, how you get your hands clean if you washed it. Hopefully you did in the last 24 hours. So how are we going to do this? You're going to determine if various substances are that you use in your life are polar or nonpolar. And this will be accomplished by determining if these substances are soluble in water, yes or no, or soluble in hexane, yes or no. If a substance is soluble in water, it's polar. If a substance is soluble in hexane, it's nonpolar. Then you'll determine some pairs based on your data. If I mix two things together, will it be soluble or not? Homogeneous, that means the same throughout. and that will be in the questions you'll have to answer. All right, if we were doing it face to face, I'd warn you, hexane is flammable like gasoline. Be careful. No, we never light any lighters or flames in an organic lab. And I would have a waste container for all your waste. Now, in part one, you'll test the water solubility of various compounds. And in a small test tube, you put about 1 or 2 milliliters of deionized water, and then you put a small amount of the liquid or solid to be tested. Then you would mix it. Now we have the vibro mixers, which have a motor and a rubber plate. You push down on it when I have it set for touch control, and it vibrates and it mixes your test tube. If you don't want to use that, which most students do because it's fun, you hold the test. I don't want to use it with my, let's do, pretend, oh, this is even better. Pretend this is a small test tube. You hold it in one hand, take 2 fingers, you go 1, 2, 3, 4, that hard. Hold it firmly. Don't tickle it because that won't mix it. Then you let it sit for a little while. Never ever shake a test tube like this because you'll get chemicals on yourself and maybe me or your neighbors. That's not good or safe. And you let it sit for a minute or two. You pick it up and you look, is it the same throughout or are there 2 layers? If it's the same throughout, it's soluble. And we call that homogeneous. If there are 2 layers, then it's not soluble. And if it's soluble in water, it's polar. If it's not, it's nonpolar. And here are the substances. And if we were face to face, this is the data you get. And we use some interesting things. Acetone, you don't have to draw the structures on this table. Acetone, baby oil, ethanol, ethyl acetate, isopropanol, otherwise isopropyl alcohol or 2-propanol, octane, sodium chloride, salt, starch, sugar, vanillin, and Vaseline. I have you do this in a beaker because it's easier to clean out than a test tube, and vegetable oil. And this is in water. Now, the other thing you would have done is done the same thing with hexane. Put about 1-2 milliliters of hexane, dry test tubes. Each time you test it, you use a separate test tube. You got to clean them out because we only have about 6 or 7 test tubes in the drawers at ECC. And you add a small amount of the liquid or the solid. You mix it never like this, either like this or put it on the vibro mixer. I like that vibro mixer. And after a minute or 2 of sitting, you pick it up and look, is it the same throughout or are there 2 layers? If it's the same throughout, it's soluble, hexane is nonpolar, and that compound is nonpolar. If it's not soluble, guess what? It's not nonpolar, it's probably polar. And here's the same charge, but now we're testing it with hexane. And if you notice, sodium chloride is not soluble in hexane, and it's not. Now, to have some fun, I also decided to let students mix some pairs of things that weren't on the list. And we have baby oil and vegetable oil, baby oil and starch, vegetable oil and starch, vegetable oil and Vaseline. I don't know why you do that, but it's fun to do. Ethanol, vanillin, ethanol, vanillin, then add some DI water. These last 2, if you have any vanilla extract, look at the label and you'll understand why I did that. And now you have the data on these tables 1, 2, and 3 to help you answer these questions. Now, listen carefully. Most students get question 4 wrong. I'm going to give you some help so you don't get it wrong. Grease is nonpolar. If you do not have any soap and you got grease on your hands, what substance that you tested in charts tables 1 and 2, I don't have that there, but those are 2 you tested, would you use to remove the grease from your hands? Now, let's talk about where students get this wrong. Question is, you got grease on your hands. I don't, but pretend I do. I've got to use something to clean it off. I don't have it on the table, but it gives you an illustration where students go wrong. Got grease, you need something non-polar, because grease is non-polar, and therefore also dirt is non-polar. I'll teach you that later on. And if it was on the list, motor oil is non-polar. Are you going to use motor oil to get the grease on off your hands so they're clean afterward? No, because after you use that, oh, the grease is not on there, but my hands are coated in motor oil. I like that. But anyways, you don't want it. So keep that in mind when you answer a question for the questions. And you know something? I'm done for today. And with that, remember, Monday, test number 3 after class, just like I've done in the past, be Monday. I'll be due Tuesday later in the evening. Also, this Saturday, I'll put out an email and also the Zoom meeting address or URL for a special Saturday morning office hour at 9. If you want to come, stop by. If not, don't. And with that, I'm going to say, gang gesund, have a nice rest of the week and weekend. I'll see you either Saturday morning or Sunday, Monday, or if you come to my office hour, because today is, nope, I'm wrong. Today's Thursday. Yes, sir. This week threw me off because we had Monday off, but I'll send out, yep, Saturday morning at 9. That's optional. And also my other class, I'm doing that, and I'll send out an email. With that, I'm done. Gang gesund. I'll see you either Saturday morning or Monday. Bye.